so the plan for today's lecture, I'm going to finish the discussion about the Dirac factors. And then I'm going to start the K-injective and K-projective resolutions. I'm going to show that in the elementary setting, for example, for in the Dirac category of the ring, they exist for any unbounded complex. And then the next thing I want to do is to show that in any Grothendieck category, any complex has a K-injective resolution. But that's quite hard theorem. It will be separated into several statements. And the key technical statement will be today. That will be a statement about the Dirac category of the ring, which has kind of a long proof, it's transfinite constructions, transfinite induction, etc. And then the next time I'm going to use this statement about the Dirac category of the ring to prove the general theorem that in any Dirac category, the forms are just sets. So that's the plan for the today's lecture and for the next lecture also. So I think this is the last theorem that I want to show in the section 4.1 about the Dirac factors. So let from translated category T to translated category T be a translated factor. So that's a translated factor. And also I fix C, the subcategory inside D, which is thick. So thick translated subcategory. Suppose that for any object X in the D, there is morphism eta sub X, so of course depending on the X, from the X to the object A sub X. So this morphism is in the more C, and object A sub X is in the acyclic category of acyclic objects for the functor F and the subcategory C. So essentially the assumption is, well, you can think of the example. So for example, take D to be homotopy category of some abelian category. C is the subcategory of acyclic complexes. Then more C is exactly the class of the quasi-isomorphisms. So essentially I'm saying that for any object there is a resolution, so there is a quasi-isomorphic object with the object which is acyclic for the given functor. So essentially the statement is, if they have a functor and for any object there is a resolution, a cyclic resolution for this functor, then there is a derived functor. So then F admits the right derived functor. Well, such that we have two additional observations. So the first one is that for any object X in the translated category D, if you compute the derived functor on the object X, you'll get the same thing as the just functor F computed on the resolution A sub X. And second property, the condition that X is acyclic for this functor and this translated subcategory C is equivalent to the condition that the map theta sub X, which is by definition the functor F, which I apply to the map eta sub X that I have in the statement. So this theta sub X is an isomorphism. So that's an isomorphism in the translated category T. Okay. So I think the meaning of this theorem is quite clear. As I explained, if you have a cyclic resolution for any object, then you can compute the derived functor using these acyclic resolutions. Okay, so I want to say that part 1 follows more or less immediately about what we already proved, right? We already know, so this follows from the fact that acyclic objects for the given function and given subcategory is right adapted. And when we prove the general theorem of the existence of the derived functor, we note that we can use right adapted objects, and if you compute functor on the right adapted object, you get exactly the functor on the original object. So the right functor of the object is the original functor of the resolution. So condition 1, just one more statement of the same thing that we proved before. For 2, we need to do something.
And when we write AFC, we mean that it's right adapted subcategory to
This one?
yeah.
No, that's by definition the class or subcategory, full subcategory of acyclic objects. That depends on the functor, that depends on the subcategory C. But usually in logical algebra there is no dependence on the C, because usually we work with the direct category and the C the class of quasi-isomorphisms. So, and we proved last time is that if you, what we proved last time is this theorem, what was the last theorem?
Yeah, that's because when you exists morphism into a cyclic object, that's why it's right adapted. Yeah,
yeah, so we proved that the intersection of the C and the subcategory of a cyclic object is the kernel of C. That's one of the first condition of the adaptability. And the second condition of the adaptability is more or less what's given in this theorem. So this is adapted, so we can use all the theory that we developed for the theory structure and see that 1 is just the restatement essentially. And why 2 is an interesting statement, well, because what I've done before, I defined this class or subcategory for cyclic objects by using just functor f without using the derived functor, which is kind of the right way to do the things, because well, usually in the elementary logical algebra, you define the cyclic objects as an object such that all the higher partial derived functors are 0. So to do this, you first need to know that it's right, right derived functor is this. And in the theory that I explained, I just first start with acyclic objects, and then using acyclic objects, I can conclude that the functor, right functor is this. So it's kind of the other way around. And the condition 2 shows that this is what you expect from acyclic objects. So the definition that you might see for the first time in the previous lecture is actually this saying that this is equivalent to the standard definition of acyclic, which is just saying that we have this property, right? Of the acyclic object, there are no high derived functors, the derived functor is the same as the original functor. Okay, so let's show this. Okay, so in one direction, so suppose theta sub x is an isomorphism. So I want to show that x is acyclic, so let S from x to the y be some morphism in the mod C. So let be a morphism in mod C. So then I already know that I have this maps eta, so I have map in this case eta sub y from the y to the x sub y. Right, so this is again in the mod C by the condition that we have. Now, the goal is to show that when I apply f functor f to this composition, I get an isomorphism. And I can see this from the commutative square. So I have f of the x, this is f of the map S, so this is f of the y. Now here I have f of the eta sub x. f of the ax, f of the a sub y. Now this is the map f of the eta sub y, and this is the right derived functor composition with the q sub s. So we have the following commutative square. So in this commutative square, well, what I know that in this commutative square, so the theta sub x, which is the f applied to the eta sub x, this is an isomorphism. Right? So this is an isomorphism, and since I know that the s is in the Morse C, I can also notice that the q of s is an isomorphism. Right? So now I can conclude, or by looking at this diagram, that f of the eta sub y composition with s is an isomorphism also. Right? So I already know that the f applied to the is this. Well, maybe I need, well, this is for any x, right? So in particular, I can apply this to the object y. So I know that this will be composition of the two, f of the eta, which is an isomorphism, then will be f of the s, right? And here, this is an isomorphism, so when I apply a functor, I still get an isomorphism. So this is isomorphisms, and these are also isomorphisms for the x and for the y. So f of the s is also an isomorphism, hence I have this conclusion. So that's the proof in the one direction. So let's go in the other direction. Now suppose, conversely, that x is an acyclic object, so it's in the a, f, comma, c. So take this eta sub x that we have in the condition, that's a morphism from the x to the a sub x.
Can you explain a little bit more why we proved the statement when we notice that f of x equal isomorphic to f of a of y?
No, I proved that this is an isomorphism.
Yes.
So that's what I started with the condition that this is an isomorphism, right? And I checked the condition that the object is acyclic. What's the definition of the object being acyclic? It means that for any map which is in the Morse C, I need to find another map, right? Which is in this case such that if I apply f to the composition, I'll get an isomorphism. So I just directly check the definition of the acyclic objects.
Yeah, of course.
Okay, in the other direction, I start with an acyclic object. I take this given map eta sub x and do the standard trick, complete this to a distinguished triangle. So let me call the new object q, and then there is a map of the x shifted by 1. So what I can notice, since this eta sub x is in the Morse C, well, this by definition just means that object q is in the subcategory C, right? Now, when this x is in this subcategory of acyclic objects, right? This is more or less by the definition of how we work with the statement is in this subcategory. So these two objects are in the subcategory of acyclic objects. But last time we proved that this is a triangulated subcategory. Hence, maybe I noticed this, since a, f, comma, c is a triangulated subcategory.
How we get that x and a sub x, y in AFC?
I assume this.
About x? Oh, also, yes.
I'm going the other direction, so I assume that x is the acyclic, right? So since AFC is a triangulated subcategory, so see the subcategory. Okay. So see the previous lecture, and x and a sub x are in the FC. The conclusion is that the Q is there, so the Q is in the A, F, C intersect with C. Hence, again, by the theorem that we proved at the end of the last lecture, when I apply functor f to this object Q, I'll get something isomorphic to the zero. So we proved that the intersection of these two things is in the kernel of the functor f. Right. So if I apply, again, going back to this distinguished triangle, if I apply functor f to this distinguished triangle, or I get the new distinguished triangle, or maybe I need to write this. So f of x, and this is theta sub x, which was f applied to the eta sub x. So this is f of the ax and f of q, which is 0. Right. So it means that this arrow in the distinguished triangle is an isomorphism. So the theta sub x is an isomorphism, and that's what we need to show in the, when we prove the other direction. So that's the end of the proof, and also of this section. So I think there are no questions, so I can erase this. Okay, so now I want to start next section 4.2, and let me call this K projective and K injective resolutions well, let me say the derived category. So I'm assuming that A is some abelian category, so this is the derived category of A. Okay, so essentially in this subsection I want to do more or less automatic things, trivial things, but what we can kind of get in this theory of the K injective, K projective resolutions for free before we do some complicated theorems. Okay, so maybe I'll start with the definition. So definition with two parts of the K injective and K projective objects. So objects first. Objects. Or maybe I need to fix notation first again. So let me maybe erase this for a second. So in this section I assume that A is of course some abelian category. So I'm going to specify conditions for this abelian category in the statements. So then inside the homotopy category, okay, there is the subcategory AC. So these are all acyclic complexes, so complexes without any cohomology. And definition now, so the first part, so objects in A C of A right orthogonal are called K injective objects, and of course the dual part is that the objects in the left orthogonal, the acyclic complexes, are called K projective. Well, first what we want to show is that for any object there is a K-injective resolution, which is a quasi-isomorphism with K-injective object, and in the kind of dual situation there is K-projective resolution. But you can note that this is very natural definition. And if you just look at the homological algebra, it tells you immediately what you need to take as a definition of a resolving object. That is because when we discussed on the previous lecture, we have a statement that if you want to derive factor for any subcategory C, right? So then the right orthogonal is kind of the class of objects that works at the same time for all factors. So here, of course, the quotient that you want to study is the derived category, and we want to define derived factors on the derived category. So this is K of A, quotient by AC of A. So it immediately tells you, that's just a general theory, that you need to find object quasi-isomorphic to the given object in this subcategory, compute on this object the factor, and that will be the right derived factor. And the same, of course, for the left derived factor and the left orthogonal. Yeah, by the way, I forget to formulate the exercise, which I should state at the end of the previous section. Take this theory that I developed for the right derived factors, take the all arrows in the opposite direction, and prove the similar statements for the left derived factors. It's completely dual theory, so kind of formally you can say that it goes into the opposite category, so it's not really interesting to repeat everything.
Yeah. So, and what's injectives of it? Because it helps to find the right derived factors. What's injective?
Injective? Well, we will see this why this is injective. Well, because essentially the idea is when you do the unbounded situation, unbounded derived categories, it's a little bit harder than the doing d minus, d plus, or db, because, for example, well, essentially you want to take, say, an unbounded complex, and you want to find, in some sense, the right resolution. Right? For example, if you don't know, you say general theory of translated categories, you would say that the resolution is just the unbounded complex of injective module objects in the immediate category. So this is quasi-isomorphic to the given complex. Well, that's just the wrong definition.
Why?
Well, it's not that kind of the acyclic class for any factor.
What if we take injective, not just unbounded complex of injective, elements for ambient category, but take well, in unbounded category we also have just in complex we have injective objects.
Yeah,
they could be unbounded.
That's the same thing.
So why we can't take injective object that's unbounded, take a quasi-isomorphism and make this as a right derived factor? Why is wrong?
No, because you need to prove theorem that you have this kind of subcategory, say, of the complex with the injectives objects, right? And you need to show that this is adapted for a factor.
Yes, that's true.
And this is not the case for every factor.
Yeah, for every. Okay.
So, but this is by definition works for any factor. So this
Yeah,
kind of universally works for any factor if you want to find the right derived factor.
Okay.
And in general, these are just different classes of the complexes. K-injective complexes is not the same thing as the complexes of the injective objects. There are examples, but I postpone these examples to the third problem sheet. By the way, the second problem sheet is posted on the Google Plus.
Yes. Yeah, and K because in homological category.
Yeah, so this K comes from this K, and there is also another maybe terminology that the K injective, also sometimes called something like homotopy injective complexes or objects. Homotopy injective and K projective. Another terminology is the homotopy projective. Okay, so that's just the definition of what kind of resolutions you're going to use in the unbounded situation. And there's also a remark which is maybe useful to sometimes to think in terms of this remark instead of just the direct definition, which when I formulated the remark, you'll see immediately that this is equivalent to the definition. So, yeah, maybe Also, I need to fix some notation. Sorry, before the remark, let me fix notation. Since we're going to use these subcategories many times, so I want to say that the ki of the abelian category A, this is by definition is the right orthogonal, so the trigonometric subcategory of K injective complexes, and Kp will be by definition AC left orthogonal of A. So this is not the standard notation, but this is kind of my notation, but this is short and kind of indicates what you consider K injective, K projective. Okay, so remark, which is just another way to formulate the definition without saying this. This kind of this definition works nicely if you look at the theory of the great categories, but if you more prefer to think in terms of the complexes, maybe this definition is better. So one, complex I is in the Ki of A, so K injective. This is equivalent to saying that for any map F from the X to the I, where X is acyclic, so any such phi is null homotopic. And the second remark, you can do this dually, right? So object P is in the Kp of A. This is equivalent if for any map phi, now you go the other direction from the P to the X, where X is acyclic, is null homotopic. As you can see, this is just, I'm getting rid of the right and left orthogonal and writing this directly in the for complexes. Okay. So first proposition. Which has two parts dual to each other. So if I take the homotopic category of the complexes bounded on the left or bounded below, with injective objects of the category as the terms of these complexes, then this is contained in the homotopic category, sorry, in the category of K injective objects, and there is the dual statement that if you have the K minus of the approach of A, then this is contained in the.
Can you explain why in this remark we have the implication from the right to the left?
From the right to the left? Well, I'm just saying that what it means here, that this condition that any map where X is acyclic is null homotopic, it means exactly that this I is in the right orthogonal.
So it means that home from X to
I is trivial in the homotopy category. No homotopic means this trivial decimal. Okay, so this notation maybe it's not clear, so I need to explain this. When I write something like this, I mean the kind of the subcategory of injective objects with the abelian category structure that I get from the category A. So in other words, this is just the complexes of injective objects bounded from the So proof. Of course, the proofs for 1 and 2 are more or less the same after inverting the arrows, so I'm going to prove only one. So suppose that I have a complex and call this complex I, so this is, well, maybe I need to fix notation. So I take a complex I in the K plus of the And since this is in the K class, I can say that if I take I with the index little I, that gives this 0 for all indices I which are less than some given index m. Okay, so let's take, using the remark, I can take a map f from the x to the I, right? So where I assume that x is a cyclic, so x is then the AC of the A. And I want to show that any such map is actually no homotopy. And I think that this is kind of very standard exercise in logical algebra, so probably you've seen this before, right? But maybe I'll do this briefly at least. So you look at the complex. This one. So then there is a second complex, which is from the K plus. So there is I sub n, there is this component f n, there's component f n plus 1 to the I n plus 1. And on the left, here, all the previous objects are 0. So we want to show that this map, assuming that x is acyclic and this is complex of injectives, you want to show that this map is homotopic to 0. That's the standard procedure for homological algebra. Just do this kind of by induction, step by step. So you take the composition of the Fn and the differential in the complex x with n minus 1, so this is 0. Hence you can factor this Fn from the xn to the image of the differential, which is embedded to the In. So then, since you have this monomorphism, image, this is dn plus 1, right? In plus 1. Right, so you have this monomorphism, so then there is...
No, that's not right. Fn not from xn to In plus 1. Fn goes from xn to In.
Yeah.
It's like that. I suppose it should be not image, but something like filter. No, it's image.
Yeah, this is of course definitely n. Well, but yeah, so just let me look at the picture. So I have this map, right? It's here, right? But since this composition, so this composition is 0, right? Yeah, so this is in the image of this, so this is differential has the wrong indexing, so this is dn minus 1.
Yeah, but what is the map from xn to image of dn minus 1? What's this map produce?
Oh, I see, this is...
I suppose there should be something like xn goes to cokernel of dn minus 1. Yes, and then to en.
xn modular the image of
Yes,
the n
xn
minus 1.
model is the image.
It is a sub-object in xn plus 1.
That's true.
So we can, since In is injected, we can lift Fn.
Yeah, so you want to say that instead of the image, I need the kernel, right?
Yeah, but it's yeah, and it's kind of the same. But cokernel.
But the kernel will be a sub-object.
And image also is some object. Oh yeah, I suppose everything's good. Yeah.
Also,
Now everything's good. Yeah. In the right part of of the test.
What?
I suppose everything's fine. So if we consider image, so we have such map and we have such.
We need to consider co-kernel of dn minus 1.
Well, the image,
Yeah, and the kernel of dn minus 1 is the same as
the image, this is a cyclic thing, so the image of this
Yes.
differential, right? So this is the quotient
yeah, so
by the image of the previous differential. So since this is a cyclic, yeah, this works.
yeah, I suppose.
So now I want to use I was using the cyclicity of this complex. Now I can use the second complex is the complex of injectives to say that there is a lift. So with H with the for the lift I want to say that I have an embedding of the image of the differential with the index n. This is embedded into the x with the index n plus 1, right? So then, by the injectivity, I have h with the index n plus 1. That is the map from the x n plus 1 to the I n, right? So this is extension of the of this map. So then we can say that the composition, since this is extension of the hn plus 1 with the differential with the number n, this is fn. So you construct kind of the first term in the homotopy, right? And then you should, well, kind of, if the only possibility here will be just to be a zero map, right? So here I constructed the homotopy and I see that this f is homotopic to 0. So for this component this works. And then you just kind of work this by induction. So I have a map here, you again use the cyclicity here, you use this net code object is injected, you construct the next map, etc. So since there is kind of the place where you can start, so there is a position n, and for this position you get zeros, you can start the induction. So I will say that by induction, there is homotopy H such that f is homotopic to 0 with this H. So I'm kind of brief with this proof because I think you've seen this before or you've done this before in the introductory logical algebra. So the whole point of the argument is that induction works because of this condition k plus, since we have 0 to some position. And you can notice that if I just remove this k plus, if they can unbound the complex of injectives, this is just not necessarily true. This argument doesn't work, and this statement is just wrong in general. Okay. So we'll project this kind of exercise to analyze everything. So next proposition, which nice thing about this proposition is I don't need to prove it. Okay, so I take object I in the homotopy category of some abelian category A, and then the following I equivalent, just kind of as a reminder. So the first condition I is K injective. The second condition is that for any object X in the homotopy category, the canonical map given by the localization of the quotient factor hom A sub AX I. So this is an isomorphism with the hom D of AX I. So condition 3, that for any roof, say WXI, so that's a roof representing map in the derived category. Say this is F and this is S, so S and F. So S is quasi-isomorphism. So for any such roof, there is map G from the X to the I, such that the composition of the GS is equal to F. And for any quasi-isomorphism from the I to the X is a section in the homotopy category.
Well, the question is, why do I know this automatically? I don't need to prove this.
You approve something like this. Just
Well,
follow
we
right
proved
orthogonal.
we proved exactly this, but for general triangulated category, and instead of the quasi-isomorphism, we just take more C. So this is just an automatic statement that we have for the derived category that follows from the general theory. So the corollary from this proposition is that if I take two k-injective objects and map from k-injective object to k-injective object, so this is homotopy equivalence, so phi is homotopy equivalence if and only if this is quasi-isomorphism. Phi is quasi-isomorphism. So I formulated this for the k-injective, and of course there is a dual statement for the k-projective. You can dualize everything and formulate dual proposition and dual corollary.
Okay. So now is another standard piece of the more elementary homological algebra. But before I do this, I need a definition. So the proof works a little bit more general situation. So I want to introduce this general situation. So a class P in some abelian category A is called smothering if, oh, I have two conditions. So the first one is kind of trivial, so this class P is closed under isomorphisms, contains zero object and finite coproducts. And condition 2 is a little bit more important. So for any object x in the A, there is an epimorphism from the P to the X, and this P is an object in this modern class.
So can you give me an example of this modern class?
So it's an abelian category.
Yeah. So this is just a class of objects in some abelian category.
Well, projective models.
Yeah, for example, if you take A to B category of R modules, then you take projective modules, they definitely satisfy both conditions. And another thing you can do is, again, take the category of R modules and take the category of flat modules.
And what is it on Russian smothering?
Я не знаю точно, как это наверное, такого в точности слова нет, но это означает, что когда вы душите человека, закрывая его доступ к воздуху, закрывая рот и нос, такое удушение, это называется смотрим. То есть это специальный вид душения.
Okay, so now the proposition. Yeah, so the whole idea is that this proposition can be proved for a smothering class, and smothering classes are a little if you have most modern classes, then, for example, just class of projectives in abelian categories, you can take free modules, flat modules, projective modules, and maybe some other examples. And also you can generalize this for the sheaves. For example, if you take the category of quasi-coherent sheaves, well, you don't have projections there, but you have flat sheaves, quasi-coherent sheaves. And this proposition works in that situation also. So the proposition says that if I have a smothering class, so let P in the A some abelian category be smothering. Smothering class. So then, for any object X, which is the complex in the C minus, so this is bounded above, bounded on the right. There is another complex, P, which is in the complex in the C minus, but the terms in this complex are objects from the smothering class. And, of course, quasi-isomorphism. F from the P to the X. So, in particular, this proposition tells us the following. If you take, say, A to be an abelian category with enough projectives, then if you take complex from the C minus bounded above, then for this complex you always have this kind of resolution of this form. But we just proved that this will be a K-projective resolution. So any complex which is bounded above, right, then it has a K-projective resolution. This is special case of this proposition. Okay. Proof. So I suppose, again, that xi is equal to 0 for I greater than n, and xn is not equal to 0. So then the construction is again by induction. So I start with the following diagram. I need some place on the top, so I have x with the index n minus 1. There's some differential to the xn, so this is differential with the number n minus 1. So then for the xn, I don't think I have enough space. Sorry. Work a little bit lower. So xn minus 1, dn minus 1, xn. So then there is object p, n, and the map, so some epimorphism, fn, right? This is because this is a smothering class. Now, to construct the next object, I do the following. I introduce object w n minus 1, which is just a pullback of these two maps, of the fn and the differential dn minus 1, so take a pullback. Then for this object, there is E with the index n minus 1, so there is some kind of epimorphism here. And then there is composition. So the composition is the differential with the index n minus 1, but this is for the complex P, this is for the complex X. So this is how I define the objects in the new complex, and notice that since this is pullback, this is an epimorphism. This map here is also an epimorphism, and the composition of the epimorphism is an epimorphism. So this is kind of the beginning of the induction, and if you want to do the general step of the induction, you will do the following. You already constructed X, say with the index k plus 1, and you want to go from the k plus 1 to the k. So then, here I have the differential d . Oh, it's important to notice one thing, so let me separate this into the two arrows. So you can take the x with the index k. So then there is a map to the kernel of the differential k plus 1. And this is embedded here. So the same is the kernel. So this is differential on the x. So then the kernel of the differential on the p. This is some object in the p in the index k plus 1. So here we have an epimorphism, and so we ignore kernels at the moment. So this composition is just the differential. So here again, I do the pullback. So W with the index k is defined as the pullback, and I take some p with the index k, an epimorphism from this pk to the wk. So the composition of these two maps, and again, so all the maps that I get here are epimorphisms. So this is f with the index k, and then I take this composition that I have here to be the differential with the index k for the complex p. So this is by definition how I construct all these pk's and all the differentials dpk.
And what is the kernels for? You just
Well, for example, you can ask a question, why this is a differential? So why the map constructed in this way are actually differentials?
Yeah, there we see it. Okay.
But for this, you can exactly look at the kernel. So if you want to say that this you have property d squared is equal to 0, then the image of this thing has to be in the kernel of the previous differential. So that's the previous differential, and since there is this factorization, the image factors through the kernel. So the kernels, the kernels in the diagram implies that the d squared for the p is equal to 0.
And WK is pullback of which maps?
Well, the same as before. The map that we
Differential and the F.
Yeah, so we do this by induction, going from the right to the left. So I assume that this map is already constructed. Here we have the differential. Here we have a pullback.
Yeah.
Exactly.
Why then WK maps to kernel of dp k plus 1 and certain, so why it's image in kernel?
Yeah, so you can check that that you can factor this like this, and also there is an induced map on the kernels, which is also an epimorphism. So to do this,
And then we should
well, to
check
do this, I think you can. Well, I think you can. What you can do is just do this in steps, right? So the pullback of these two maps, right? You can take this pullback, and then you can take this pullback.
Yeah, and what? The first one pullback should be kernel, yeah? Yeah, that's probably true.
Yeah. Well, there are several statements about the abelian categories that I'm not going to verify. So this one of the statements. So I can assume that you know abelian categories and just use this. You can verify this. We can work on the level of the elements and then use the Mitchell phrase embedding theorem, or you can try to do it directly in any abelian category. But that's what you get if you do the computation.
Also, so we need to check that the map, the induced map on kernels is subjective, and then take a pullback of this map.
Yeah. Yeah, but this is just a general property of the pullbacks. You can take this big pullback as these two small pullbacks. This is how pullbacks work in general.
So we need then to prove that the right-hand square is a pullback, where kernels and...
Oh, you need to show that if you have this embedding and you have this map, right? If you take the pullback, well, of course you have the epimorphism, but you need to check that the object that you obtain here is the kernel of the differential. Which I think is, if you do this for the elements, it's not that hard, it's more or less immediate. Okay, so this is how we define the objects, pk, and the differentials. Now
I need to show that this is a quasi-isomorphism, right? So the last part is to show this is quasi-isomorphism. For this I need another couple of diagrams, but let me start with the following. So there is a canonical map from the co-kernel of the differential of the x with the index k minus 1 to the kernel of the differential with the index k plus 1. We can notice that in any complex we have such map. And the question is, what's the kernel and co-kernel of this map?
For x.
Yeah, so this is for x. Oh, well, this is actually for any complex.
And there's k minus 1 and here k plus 1.
Yes.
Well, it's cohomology.
Yeah, exactly. So the
Yeah.
kernel, this is just the cohomology. So the kernel is the cohomology with the index k for the complex x.
Mm-hmm.
And the co-kernel is the cohomology with the index k plus 1.
Mm-hmm.
So another little exercise that I'm going to use here. Okay. So then I use this map that I introduced before. So there is a kernel of the dp with the index k plus 1. So where I have this epimorphism from the previous diagram. And then again I take a pullback here. So I'm going to call the pullback t with the index k. So again, this is defined as a pullback of the two maps. Well, and now this is another general property of abelian categories. So if I have a pullback, right, so then I have, let me call this map in the pullback phi with index k. I also can kind of write the kernel of this by k and the co-kernel of the phi k. So I have a sequence like this. And the general theory of abelian categories tell us that the induced map on the kernels, if you have any pullback square, then on the kernels you always have an isomorphism.
Mm-hmm.
You can verify this. This is a property of a pullback in abelian category. For the co-kernels, in general, this general theory just tells you that on the co-kernels the induced map is a monomorphism. It's not in general an isomorphism, but in this case this is of course an isomorphism, right? We only need to check that this is an epimorphism, but if you go like this is the same as going like this, but this is epimorphism, this is epimorphism. So this composition is an epimorphism, usually. Hence, in this composition, this map has to be an epimorphism. So in fact, it's not just a monomorphism, which is kind of given in general, but this is another isomorphism. Okay.
Why it is a monomorphism? So it is.
Theory.
Well, you took that class when I discussed abelian categories.
Yes. So it is just a property of.
Just one of the lemmas that I took in that course. But in this course, this is an exercise on abelian categories. Okay.
Yeah, but that doesn't prove that this is homology of.
Sure, this is just the beginning of the computation. We need to do some other things. So we need to compute cohomology, say with the index k plus 1 of the new complex P. Well, this is more or less by the definition of the cohomology, the co-kernel of the map pk to the kernel of the differential with the index k plus 1. Right? So then I claim that I can take this co-kernel and write this a little bit differently. This is again the co-kernel of the map tk to the kernel of the s k plus 1. This is not s, this is differential. dp k plus 1. Right?
No, what is it wrong?
Oh, well, for this we need another diagram. So we have x, k. There is an epimorphism to the co-kernel of the dx k minus 1. Then
this is a map to the kernel of the dk plus 1. So here we defined object tk, right? So here there is a kernel. So the same diagram. So dpk plus 1, right? But this is embedded, of course, in the pk plus 1, and there is a map. Yeah, and then I can take pullback one more time, and if I do this, so this is a pullback, and this diagram is also a pullback. So if I compute this pullback twice, I'll get exactly this pullback square, right? So it means that the object that I obtain by taking pullback twice is precisely the wk. Now from the w with the index k, by the construction, there is an epimorphism with the pk, right? And then you can see that you're interested in the co-kernel of the map. So this is the kernel, right? And then there is a map pk, right? You're interested in this co-kernel from this long map with which is the composition of the three maps. And then I claim, well, since clearly this is an epimorphism and this is pullback, this map is also an epimorphism. So in this composition of the three maps, we have two epimorphisms, hence the co-kernels are the same. Hence this is true.
Yeah, that's true.
Okay, so we compute this as this co-kernel. Yeah, and the co-kernel of the map from the tk to the kernel, which is just this map phi k, which I introduced before, the co-kernel is isomorphic to the cohomology hk plus 1. So this last thing is isomorphic to the cohomology with k plus 1 of the x. So that's a quasi-isomorphism, and that's the end of the proof. Okay. So, kind of the complementary proposition. Complementary proposition tells us the following. So, as before, I assume that I have a smothering class. So let P be a smothering class. I assume that I have two objects, x and y, in the C minus of A. I assume that I have a map F is a map between these two objects, so map of complexes. And I also have a quasi-isomorphism, so U from the P to the X is quasi-isomorphism, and the object P is in the C minus of this modeling class. So I kind of have this resolution. So then there is commutative diagram. So there is a commutative diagram where we have resolution P, which is mapped using map U to the object X. From the X to the Y, there is map F. And I'm claiming that there is a resolution Q for the Y and the induced map M between the resolutions. So there is a commutative diagram, and in this commutative diagram, Q is in the C minus of this modeling class, and V is quasi-isomorphism. So this proposition is saying that behaves almost like a functor. Well, you can take an object, you can replace this by the resolution, and there is also a map on the resolutions.
So the standard things that we prove for project objects, but for most larger case, like smoothing class.
Yeah.
So the proofs are kind of the same.
Well, if you know these proofs, yes.
So this, if you study, say, projective objects and you consider the case of the D minus, everything is more or less standard. It was done in the 60s. But we still need to do this kind of elementary theory because the general theory is built on this theory. So for the unbounded complexes. Yeah, and resolution. So these properties of the resolutions can be shown in a little bit more elementary way using more about generated categories. So I can take the composition of the F and U and construct the following distinguished triangles. So I have P, then the composition of the F and U. This is mapped to the Y. So I want to complete this distinguished triangle, so call this object C, and I want to call this object C shifted by minus. So I have this distinguished triangle. So in the distinguished triangle, I can choose, since I know what exists, so H is quasi-isomorphism, and T is in the C minus of this modeling class. Oh, I already know that I can always find this. So I take C shifted by minus 1 and take this resolution from the C minus of this modeling class. Right? So then I consider the following map, right? So this map from the T to the P is just the composition of the map H that I just introduced, and this map from the distinguished triangle. So then I can complete this to a distinguished triangle, call this third object Q. So the map that I obtained here M, and there is also map V here. So this is T shifted by 1, and this is H shifted by 1, right? But then again, since we know that the P is in the C minus of this modeling class, T is in the C minus of this modeling class, we can conclude that the Q is in the C minus of this modeling class. By the way, this is not a completely trivial statement.
Yeah, that's true. And that's not a completely trivial statement that C is in C minus of A.
C?
Yeah.
Yeah, that's also.
And that's when we say that we take T such that this is quiz, we consider C as a C minus of A. So that's kind of little moments.
So, maybe I need to add it here. So C that I obtained when I complete the triangle, this is in the C minus. Okay.
That's all. Well, that's all follows from that we can consider the soul in the whole complex in just homotopy category, and consider subcategories that have homology only in that bounded above. So we can consider
You want to invoke some triangulated categories and say that this is standard technique for the triangulated categories.
yeah.
But I have a little bit different explanation since we work in the homotopy category, and triangulated structures in the homotopy category we know explicitly. Right? So when we complete the distinguished triangle, we just take the column of the morphism between complex. And since these two complexes are in the C minus, this is also in the C minus.
Mm-hmm.
And the same also works here. These two complexes are in the C minus, so then the column of the morphism is also in the C minus.
Mm-hmm.
So it's easy, but not entirely mathematical. So Q is in the C minus, and and so the last observation is that the V that we have here is quasi-isomorphism. So, and I think that we proved this in general.
Mm-hmm.
So V is the quasi-isomorphism, and that's what we need, right? So this commutative square is more or less the same commutative square that I promised there. Okay. Okay, so then we've done all the technical work in the case of the modern class. Of course, you can dualize everything and introduce the notion of the postmodern class. You need to change the second conditions. Instead of the dimorphism, you get monomorphisms. The rest is the same, and the proofs will be the same, so we can dualize everything.
So, do we know such thing that under making pullback, the monomorphism goes to monomorphism? We have such. So if we have a pullback diagram, like there are VK, TK, XK co-kernel, and like from XK to co-kernel we have monomorphism. Is VK, WK to TK monomorphism? Is it true?
You want to say that M is monomorphism.
Who?
M is monomorphism, right?
I don't know. Who is M?
M is the
No, I just said that when we work with the smoothering class, we use the thing that under pullback, that surjection under change of basis goes to surjection. Epimorphism under change of basis.
Epimorphism is an epimorphism.
Yes. Is it true for monomorphism?
Push out for monomorphism.
Use push out, yes.
You dualize everything, so the pullbacks will get push out.
Yeah, that's true.
Yeah, but also this remark that if you want to notice about M, we can also notice interesting things. That this M, since this is the form of the morphism, you can notice that M is always a monomorphism in this construction. And in fact, since this is a form, this is a semi-split monomorphism. So this M has additional properties by the construction, which are not important at the moment. Okay, so what I want to say is kind of elementary corollary. So if abelian category A has enough projectives, so and you take object X, which is in the C minus of A, so then there is an object B, which is in the C minus of the approach. Okay, and quasi-isomorphism from the B to the X. So you have enough projectives that any complex bound on the right has a projective resolution in the most naive sense, such that a complex such as each term in this complex is a projective object. And you already know that this will be a K-projective resolution. But we can see that if you're interested in the, say, building the derived category, maybe I formulate this as a second corollary. Again, the same assumption, A has enough projectives, so then the derived category D minus of A is equivalent as a translate category to the K minus of the approach of A. So in particular, D minus of A is locally small. So what I want to say that in the case when you restrict your attention to the D minus and you have enough projectives, then the theory is more or less trivial, right? You can use elementary homological algebra to construct such resolutions, and then have this conclusion that this derived category is just the same thing as a homotopy category of projectives.
Yeah. What does locally small?
It means that the Holmes form sets.
Isn't it just small?
No, small means that the object
Oh,
sets.
the object, yeah.
Why it is locally small?
Well, because I can identify this with the homotopy category, and in the homotopy category, all the homes are small by construction. You take a set, take a previous relation of the set. Okay.
Okay, maybe it's a time for a break. So let's take a break and then continue after the break. What we can say if the categories are involved.
Правда, что при пулбеке ядра изоморфны?
Что?
При пулбеке ядра изоморфны.
Да.
То есть, поэтому если был мономорфизм с одной стороны, то тогда он с другой.
Да.
И эпиморфизмы тоже при пулбеке сохраняются.
Да. Я думаю, что все так.
То есть все сохраняется, и мономорфизм, и эпиморфизм получается.
Что при пулбеке мономорфизм
Но
сохраняется.
если ядра изоморфны, то да.
Да. Если ядра изоморфны, то если это был мономорфизм, то он останется мономорфизмом.
Действительно, кстати. Ну ладно.
Ну, по-моему, это так.
Сейчас на странно, как сейчас. Странно, причем, типа, ко-ядра не изоморфны. Но эпиморфизм сохраняется. То есть при пушапте в идеале тоже получается там и эпиморфизм, и мономорфизм сохраняется. Немножко странно. Но
Нет, вот это свойство четко вызывает подозрение.
Да,
Немножко сохраняется.
Нет, но если ядра изоморфны, то
ну, все логично, просто странно.
Да.
Просто да, мне, кстати, кажется, я вот что-то не уверен.
Сейчас, да. Ты точно думаешь, что ядра изоморфны? Может, на только отображение в каком-нибудь есть? Типа эпиморфное?
Ну, отображение вроде точно есть.
Да.
Сейчас вам.
Ну, нормально.
Мне кажется, там справа наоборот, это, там справа изоморфизм, а слева, да, мне кажется, там все-таки ко-ядра должны быть изоморфны, а ядра не факт.
Нет, ко-ядра точно не изоморфны, это я 100% помню, на ко-ядрах мы можем в общем случае сказать, что у нас есть мономорфизм. Но мне кажется, кстати, может быть, я неправильно сказал, может быть, на ядрах у нас не будет изоморфизма, но это и не важно, потому что в вычислении я пользовался только вот терминологией ДСМ-1, это ко-ядра.
Сейчас, ну подождите, но там же есть такая ситуация, что если у нас есть, ну вот, если у нас есть вот этот вот пулбэк, мы строим конусы, конусы должны быть изоморфны. Нет, ну вроде, смотрите, ну если у нас есть мономорфизм, да, вот я вспомнил, там, если у нас есть мономорфизм, вот так вот, и сверху еще одна.
Если у вас два,
то это пулбэк.
Пулбэк двух мономорфизмов, да.
Не, беру, вот смотрите, у нас есть точная последовательность, короче. Да, вот, когда у нас есть точная последовательность, вот здесь, да, наверное, да? Следующее.
Что можно сказать?
Ну, пока да. Если у нас есть точная последовательность, там 0, А, Б, С, 0. Мы можем вот здесь вот сделать D, вот здесь вот W, fullback. Вот это вроде мономорфизм, а вот здесь C. Ну, то есть это что-то общее, что это полное, да?
Я думаю, это несомненно.
Вот. Ну, значит, ко-ядра изоморфны, нет?
нет, там...
Но это не совсем правильный сейчас.
Диаграммный лем. Там при пулбеке сохраняется всегда мономорфизм, и ядра изоморфны. А если одно из отображений является эпиморфизмом, то он тогда Декарт, не только Декартов, но и ко-Декартов. И поэтому сохраняется и эпиморфизм.
Поэтому и ядра изоморфны.
Да. То есть получается...
Что говорит, то есть ядра изоморфны?
То есть если в декартовом квадрате одно из отображений, которое снизу оно является эпиморфизмом, то он...
Ну да, или вот это эпиморфизм, то ко-ядра изоморфны.
Если это эпиморфизм, да. То есть если из А в Б или из Д в Б здесь был бы эпиморфизм, то были бы ко-ядра изоморфны.
Но вообще тут так и так ко-ядра изоморфны. Ну вот эти ко-ядры.
Мне кажется, надо говорить про двойственное друг другу утверждение. Потому что у вас здесь как бы вы берете pullback с мономорфизмом, а вы хотите pullback с эпиморфизмом.
Не, ну это Николай говорит про это, про вот нашу ситуацию. Я-то просто сказал это в пустоту. А про нашу ситуацию, где вот вы сказали, что ядра изоморфны, и вот вроде ядра изоморфны, да?
Да, ядра всегда изоморфны.
Да, ядра всегда изоморфны, а ко-ядра не всегда. Но если эпиморфизм хотя бы один есть, то ко-ядра изоморфны.
Да.
Вот, но это вроде да, это вроде то, что...
Нет, мы все равно получаем, если ядра изоморфны, то pullback мономорфизм.
Да, что странно.
Что вызывает подозрение.
В Википедии так и написано.
Что именно?
Ну, что морфизм сохранится. И это что написано.
А
А
эпиморфизм?
в Википедии написано.
Но про эпи это только для абелевой категории. То есть там,
Pullback от эпи.
если есть декартов квадрат и там есть эпиморфизм, то это кодекартов квадрат.
Нет, скорее вопрос, правда ли, что pullback от эпиморфизма эпиморфизм?
Ну, в общем случае, видимо, нет.
А в абелевой категории?
В абелевой, да.
Почему?
Ну, потому что тогда квадрат кодекартов для кодекартов
А, и
это-
тогда эпиморфизм сохраняется, да ладно.
То есть в абелевой категории, да, вот просто получается, что это точный квадрат.
Да, да. Вообще идеальный квадрат. Да, окей.
И к-ядра, видимо, в таком случае изоморфны.
Ну да.
А это получается, что там есть двойство, да? То есть если у нас в пушауте есть мономорфизм, то это и декартов, и кдекартов.
Да, полбэк автоматически превращает полбэк в пошел.
Ну ладно. Да, я, кстати, еще немного сомневаюсь, но в том это утверждении про то, что когда у нас вот такая ситуация, где там вот ядро, да, ну вот фи какого-нибудь, вот оно вкладывается вот там у нас в x, да, вот здесь у нас p, и тут типа, ну там p, давайте 1, 1, тут p2, x2, и вот ядро вот этого. Вот. Ну, у нас там такая с дифференциалами, да, ситуация. И вы говорите, что вот pullback этого, ну вот здесь фи-штрих, это ядро фи-штрих. Вот я что-то немного сомневаюсь в этом. Это вообще...
Нет, по крайней мере, можно здесь сказать, что ядро фи', оно сюрреактивно отображается в ядро.
А вот это можем сказать?
Это можно, да. Ну, потому что мы...
Вот, кстати, это вот для этого достаточно доказательства. То есть я мог быть утверждение, что это полгода, как бы я погорячился, это неправильно. Но утверждение, то, что у вас там будет эпиморфизм, это, наверное, все-таки верно. И то, что у вас будет, ну, вот у нас там еще два объекта, которые...
Ну и мы достаточно взять вот в этом pullback, да, и все?
Да, я просто мне нужно показать, что как бы эта стрелка, которая вверху появляется в pullback, она проходит через ядро.
Ну да.
Так, чтобы сказать, что дифференциал в квадрате равен нулю. Да, наверное, с полбаками здесь я тоже погорячился.
То, что на ядрах эпиморфизм, это следует из того, что если бы мы никакой P не доставили, а просто взяли бы от W, там был бы изоморфизм на ядрах.
Ага.
А тут мы берем P еще, накидываем на W, и от этого ядро только больше становится. Поэтому эпиморфизм.
Окей.
Вот в домашнем задании я видел задачу там доказать, что если А категория Grothendieck, то и С та категория Grothendieck. А у категории Grothendieck мы используем определение, что это АБ5 и есть один проективный генератор.
Да.
То есть именно один.
Нет, не один проективный генератор, а один генератор.
Один генератор. Просто не обязательно проективный.
Не обязательно, конечно. Но если бы был проективный, то это была на самом деле категория модулей.
Да. Но он именно один, то есть не семейство, а один.
Да, именно один, потому что на самом деле категория Grothendieck у вас есть все произведения.
То есть это как-то можно отдельно доказать? Или пользоваться этим можно?
Но это можно доказать, если вы как бы вернетесь опять же к тому курсу, который я не доказывал, и доказательство там типа строчку занимает.
Нормально.
Скорее всего, кстати, это было управление семинарами, мне кажется.
До свидания.
До свидания.
просто это мы доказывали, что если в категории Grothendieck все произведения существуют,
Да.
то, что она АБ3 звездочка категория,
Да.
но при этом не обязательно АБ4 звездочка.
Не обязательно. Ну, насколько я понимаю, вот как раз категория квазиконечных пучков это не АБ4. Например, то, что видно категория квазиконечных пучков на другой схеме, это категория Grothendieck.
Хорошо.
Ну, и эта теорема совсем не издумана. Grothendieck это было доказано только в 2005 году.
А в чем она проблема была?
Ну, да, проблема была в том, что это будет кому неинтересно. Просто что если у вас есть там какая-нибудь квазиотделимая, квазикомпактная схема, то на ней тогда квазиконечные пучки образуют категорию Grothendieck. Мне кажется, это что-то такое очень старое, как раз из времен Grothendieck. Но ну, это как бы тоже полезно для практики.
А, в смысле, для любой схемы?
Да, вообще для
неизвестно.
любой схемы.
Ну,
Никто особо не интересовался, но тем не менее это правда.
да, тогда понимаю, почему никто особо не интересовался.
И, кстати, даже есть какое-то, ну, такое поверье, я несколько раз встречал людей, что ну, люди думают, что для производной схемы могут как-то наклеить нехорошо, что она будет не Grothendieck. То есть это общее такое, как бы, фольклорное знание, что существует контрпример, это неправда.
Сейчас производная схема. Что вы имеете в виду? Производная схема?
Производная схема, которая плохо склеена.
Нет, ну в смысле, ну там много категорий. Ну, вот вы говорите, что квазиконечная будет Grothendieck, а когерентная.
Когерентная не может быть
Не
Grothendieck,
может.
потому что там нет никакого разделения вообще, там она даже не АБ3, АБ3 звездочка.
Да, действительно, а у X модулей?
Как смотрим всегда, это очень простое утверждение.
Ага.
Okay. So let's now go to the unbounded situation. So proposition let A be a Grothendieck category that's important for the group. E inside A is a smothering class. So then every complex X admits quasi-isomorphism of the object P to the X. So where I can take this object P to be in the smallest localizing subcategory, so localizing closure of the C minus of the P. Okay. Proof. Well, we know that this holds for the C minus, right? So I can take the following. I can take the truncation tau n of the X, right? So this is now from the complex from the C minus, right? And for this complex, I can take the resolution. So there is a resolution Pn. So this is quasi-isomorphism. And Pn, I can choose to be in the C minus of this modern class by what we proved before. So then I have the following diagram. I have P0 is quasi-isomorphic to the truncation at level 0 of X. Then this truncation is harmonically mapped to the truncation at the level 1. This is mapped to the truncation at the level 2, etc. So here I have P1, here I have P2, and I know that I can also induce maps on the resolutions by this complementary proposition that I proved on the previous part of the lecture. So we have to
to directed systems, right? And then I can say by definition that the object P that I want to consider in this statement is the homotopical limit of the Pn's. So, since these two directed systems are quasi-isomorphic, then the P, which is homotopical limit of the Pn's, is quasi-isomorphic to the homotopy colimit of the truncations of the complex X. Now, this homotopy colimit I can actually compute, so there is a map which is quasi-isomorphism to just the directed limit of the truncations. Why there is a quasi-isomorphism of this from homotopy colimit to the just ordinary colimit?
Well, because of Grothendieck.
Yeah, this is where we use the assumption that A is Grothendieck. And then finally, the straightforward computation with the truncations show that this is just isomorphic as a complex to the X. So this map is indeed a quasi-isomorphism from the P to the X.
So, and there is a P quasi-isomorphic to this Hochuli.
Here?
Yeah.
Yeah, this is quasi-isomorphism because all these maps are quasi-isomorphism. So if we compute the, well, in general, if we take a triangulate category, we really have to do directed systems. If they are isomorphic term-wise, then the colimits are, of course, isomorphic. This immediately falls from the definition of homotopy colimit. Yeah. So this is how we construct this, and the last question we need to analyze why this object P that we constructed is in the log C minus of P. So do you see this?
Log closed under taking for colimits.
Yeah. So because this log closed under homotopy colimits, this is in the log C minus of the smoother class. So this is how we can construct the resolutions of the unbounded complexes. Let me formulate maybe as a corollary the following statement. So if A is the Grothendieck category, so Grothendieck category with enough projectives, so then any complex admits a K-projective resolution. Okay, so maybe I need to say something in the proof. It doesn't immediately follow, right? Because I don't, mainly because, well, I can do the same procedure, right? I can take the truncation for each of these truncated complexes. I can find a resolution with the projective terms, which is also from the C minus, and we can notice that if we prove as before, and notice the following, that Pn is in the, by the what we proved before, is in the Kp of A, right? Since this is in the C minus and each term is projective, this is homotopy projective, right? And then since we define this as the right orthogonal to the acyclic complexes, this is automatically, sorry, left orthogonal. So this is left orthogonal, this projective situation. So this is automatically localizing.
Yes, that's true.
Any left orthogonal is localizing. Hence, the Pn which is again defined as a homotopical limit, so B, which is homotopical limit of the Bns, this is in the Kp of A. So this is localized. So this is the reason why this works. Well, you can take the same proof and it still works. Yeah, so there also may be an interesting remark what's going on here from the point of view of the theory that we developed in the beginning of the course. So I'll continue to assume that this situation, A is Grothendieck with enough projective objects. So then I have AC of A. This is a subcategory in the homotopic category of A, and then there is a quotient category, which is the derived category, right? What we proved is that both these functors admit left adjoints. So these are left adjoints, right? Why we proved this? Well, this is because I can take an object, right? I can find the K-projective resolution, so there is a quasi-isomorphism here. Hence, if I complete this to a distinguished triangle, I'll get some Q. So this is in the K. Maybe I write this instead of Kp. I just write this as the AC of A with the left orthogonal. This is acyclic, since this is a quasi-isomorphism, so this is in the AC of A. Well, then there is P shifted by 1. So for any object, I constructed such a distinguished triangle where this is in the left orthogonal and this is in the just subcategory. So remember the theorem that we proved in the first weeks, where it was 6 statements are equivalent. That was for the right adjoint functors, but of course there is a corresponding statement for the left adjoint functors. So if we have such distinguished triangle for any object, it means that I can find the left adjoint functors for the embedding and for the quotients. And in particular, I can also notice that
So how we construct Q? Well,
I take a resolution and take a distinguished triangle. So I can say that also in this case, yeah, so the derived category in this case, this is equivalent to the left orthogonal complement to the subcategory, which is the homotopic category of projections. Okay. So I'm still using this theorem with 6 points, okay, the dual version of the theorem, because here the triangle is like this. This is from the subcategory, and this is from the left orthogonal of the subcategory. So it means that I have these adjoint functors for the both of these functors, and also have a description of the quotient category as the left orthogonal to the subcategory. And another consequence of that is that this category is locally small, since this is realized as some homotopic category. And also you can notice that, well, maybe if you call this functor Q and the adjoint functor, maybe you call little r, temporal notation, then the canonical map, the counit of the adjunction, so the QR of x to the x, this kind of the canonical projective resolution for any kind of factorial K projective resolution of any object x. As you can see, this kind of works nicely because basically you start with the definition of the derived category, right? And you just analyze the definition. For example, we know from the general theorem that if you have some adjoint functors, then we can kind of say something of this kind. And this is what we obtain here. So we just, if you can think about this as, well, you can start with elementary homological algebra and kind of build everything up from the elementary homological algebra using the resolutions from the C- and this argument to get unbounded resolutions. Or you can kind of start from the translate categories take this exact sequence of triangulate categories and ask, do you have a left adjoints or the right adjoints? So in the left adjoint case, if you have enough projectives, you have the adjoints, and this automatically give you the kind of the description of the derived category as the left orthogonal, kind of give you the right notion of the resolution, and also automatically give you a factorial right resolution. Okay.
Does it have this isomorphism due to existence of adjoint functors, or from
Which one?
between DA and orthogonal ACA?
Oh, you remember there was a statement with 6 equivalents? Well,
Yes, yes. So we use that statement.
yeah, do to that statement.
Yes.
Yes.
Is there a right orthogonal?
Yeah, right orthogonal is by definition the A injective. So in the good situation, you have two orthogonals. For example, if A is just the category of R modules or subring, then you have two adjoint
Does
functors.
it have enough projectives and enough injectives?
Yeah. So that's kind of tricky part. So remember this proof. You kind of want to take this proof and you want to dualize everything. But what you get is quite weak statement. So let me erase this and probably what you get. So when you dualize everything, you get the following proposition. So proposition. So let A be an abelian category with exact products. So this is AB4 with a star. And projective generator. Then every complex has a K-injective resolution. So if you just dualize the proof that I just erased on this blackboard, you notice that instead of abelian category, you need assumptions of this kind. Exact products, no, because of the co-products, you need to use products now, and to go from homotopy limit to the homotopy limit to the ordinary limit, you need some additional properties like the existence of a projective generator. So essentially, this is built on the last exercise of the second problem sheet. So this is kind of explains why you need such conditions. So you can try to generalize all the arguments. That's what you get. As you can see, this is kind of what we get for free without any hard arguments. Because so I consider what we've done so far in this lecture is kind of elementary arguments. But you can see it's not very satisfactory, right? Because in the applications, like when you want to quasi-coherent shifts on the schemes, well, there is definitely no projective generator. Well, and also the products are not exact, so both of these assumptions is not very useful in the applications. So what I want to show is that if A is any abelian, is any Grothendieck category, then every complex A has K-injective resolution. As you can see, this is not a trivial statement, it doesn't follow immediately from the general considerations. So let me, with this, start new section. So this will be section 4.3. Say K-injective resolutions.
Exercise sheet?
No, the proof is more or less the same because the dollars the proof that was here. But you notice that at some moment you need to go from the homotopy limit to the ordinary limit, and this doesn't hold in any abelian category. You need some assumptions. So before was coordinates, and the assumption was that the category Grothendieck. Here the assumption is these two things: exact products and projective generator.
Yes. And
So,
after dualization, we get enough conditions to claim that homotopic limit is equal to simple limit.
yeah, dualizing the previous argument plus using these additional categories, it's enough to guarantee that the elementary proof that was here works in the dual situation. So K-injective resolutions for Grothendieck categories.
Yeah, and the last statement that A is Grothendieck with enough project, it's not. It's also not what we have in our skip situation.
Yeah, because we don't have enough projectors.
Yeah, so we in skip situation we just use enough flat models and
Yeah, that's the
work with
reason
that.
why I talked about modern classes, because flat models forms modern classes. And for example, if you want to derive tensor products, you already have a theory for this.
So we can say that's not have enough projectors that it has a smoothering class. Not smoothering, just smoothering class.
Yeah.
Okay. Mm-hmm.
Yeah, and notice that using this proposition, for example, if we take the derived category of the ring, then we already know that everything is fine. So this kind of every unbounded complex has K-injective resolution, it also has K-projective resolution. Or in other words, in that kind of embedding a quotient, there is both left adjoint and the right adjoint factors.
Mm-hmm.
Okay, so I start with the proposition, which is kind of the main technical proposition for this whole section, and this section is probably one of the technical main ingredients of the whole course. So the statement is the following. So let E be just a complex over some ring R. So I'm not going to write that R is a ring, so take a complex over a ring. Consider L to be the localizing closure of one object. So then there is localization or localizing factor, so little l, such that this category L is the kernel of the little l. So this is the statement that we need to prove. So in this special case of the derived categories over a ring, everything is nice. So again, you can notice that one of the conditions of these 6 equivalent conditions is satisfied, and namely the first one, if you have this. Okay, proof.
Can you recall what is localizing factor?
Well, that was the some and the functor in this case from the derived category of the ring to the derived category of the ring, right? It also has a map. So is this map from the identity to the L? So and the L squared is the same as L.
Okay, thank you.
There's the second one. The second condition is what?
So there is a natural transformation of functors from the identity functor to the given functor L.
Okay.
So ID is mapped to the L.
Mm-hmm.
Okay. So first observation is that without loss of generality, I can assume that this object and all its shifts are K-projective. It's K-projective for any integer K. And since this is the case, if I want to complete the form in the derived category of the ring from the EK to some other object X, I can as well just compute the form in the homotopic category of the ring from the EK to this object X. This is for any X. So what I'm going to show is so I have this theorem with 6 equivalent conditions,
and I want to conclude that the first condition holds, but verify the last condition, the sixth condition. So what I want to show is that for any m in the derived category of the ring, there is a distinguished triangle with the n sub m, which is mapped to the m, and then there is object Bm in the distinguished triangle. So in this distinguished triangle, n sub m is in the subcategory L, and B sub m is in the orthogonal, so the right orthogonal. Right? If I can show that there is such a distinguished triangle, I'm done. Unfortunately, this is not very easy. So I'm going to separate this into 3 steps. So step 1. So let me call this definition or construction. Definition of the Bn. So I want to propose a definition of this Bn and then check that all properties are correct for this definition. Okay. So let me assume that at the moment I is any well-ordered set.
So the theorem that you talked about is big, yeah, the big theorem with a lot of transfinite reactions.
Yeah. So, and then we construct objects Bi for little I being in this well-ordered set by transfinite induction. So, construct so the definition, of course, for the B0 is just to be M. So then we need to consider 2 cases. So if for say S in the set I there is a predecessor, so let me just shortly write this formula. So there is S minus 1. So we assume that by induction I already constructed Bs minus 1. I want to construct Bs. For this, I define set omega with the index x minus 1, and this is just the disjoint union over all integers of these sets, which are wholes from the E shifted by k to the Bs minus 1. So then we automatically get a map. So there is a direct sum over omega s minus 1 of the E k to the Bs minus 1. So let's call this map alpha with the index s minus 1. Right? Well, clearly you have this map, right? Because this is a map from the coproduct. We need to define this map kind of for each component and the embedding of each component, but this is defined tautologically, right? Since each component is parameterized by such a map, so you just take this as a map. So by tautological reasons, we have this alpha with the index s minus 1, and we complete this to a distinguished triangle. So then we'll get object Bs, and I'm going to call the map that I obtain here a map with the indices mu, s minus 1, and s. So I'm going to construct some directed system, so this will be a map in this directed system. So then there is kind of continuation, but it's not important, so just pause 1. And we can also notice that the maps that I constructed here, so mu with the indices s minus 1 and s, these are semi-split monomorphisms, right? Because this is just a maps to the cone of the map between 2 complexes.
isn't? Can you repeat the argument by semi-split model?
Well, because this is a map to the cone. Right. So this is semi-split monomorphisms. But this is just a map between kind of object and its successor. I want to say that all the maps between all the BIs are at least monomorphisms. Well, in fact, they are semi-split, but what's important, they are monomorphisms.
You use the explicit construction of cone in homotopy category.
Yes. Yes. Well, this is everything very explicit because I just work with the derived category of a ring. Okay, so. And then, if I consider, say, I, which is smaller than S, then the map mu with the indices I and S, I can write this as a composition of the S minus 1S. So this is kind of the definition, if you want, for these new maps. Right. So I assume that for the S with S minus 1, I already constructed all such maps, so I construct maps with the I and S as such compositions. And again, by the induction hypothesis, I can assume that this is semi-split mono. Okay. So then I have the following. If I take a map F, which is just a map from the E shifted by K to the some BI, where I assume that I is less than S. So then the composition of the mu I, S, and F is 0 in the homotopy category of the ring. So why this is the case? So this is by construction for I equal to the S minus 1, and by induction for I smaller than S minus 1. So I'm constructing this directed system of the BIs, and on each step I want these properties that the maps in this directed system are all semi-split monos, and if I take a composition with any map in the home, I'll get something homotopically equivalent to 0. But so far I constructed this only if S has a predecessor. So I also need, since this is transfinite induction, also need to consider the limiting case. So if S, which is now element in the I, has no predecessor, so then I'll set, just by definition, the object Bs to be equal to the co-limit of the Bi's, where I is strictly smaller than S. And the maps are also defined as the co-limits, so the mu Is is co-limit of the mu Ij, where I is less than J and J is less than S. So this is a co-limit which I just take in the category of complexes, and maps that I have here, maps mu Is, you can notice this is just the maps in the limiting call. No, but formally you can define this by these two formulas. Okay. So then we have a triangle like this. So Bi is mapped with the mu Ij to the Bj, and then there is this Bs, which is mapped to the mu with the map mu Is, and this has mu JS. So let me, as before, assume that I have F. This is just a map from the E shifted by K to the BI. So then, clearly I have the following formula. Composition of the mu with the indices I and S and the F is equal to the composition of the mu with the indices J and S and the mu with the indices I and J and F. Oh, that is because we have this mu I, J, F. They are all kind of homotopic to 0 for all the indices. Hence, mu I, S, F is also homotopic to the 0. Okay, so that's the directed system that we constructed. Well, I need to erase this for sure.
Just colimits, so it's not homotopic colimits.
No, this is I understand this is colimits and the category of complexes. So almost colimits of complexes.
Mhm.
So this is the directed system that I constructed by this transfinite process, and it has by construction several properties. Well, semi-split, but I don't think that this is very important for the rest of the proof. It's important to note that these are monomorphisms. And also we have this property that if you take a composition, so if you take a composition of the mu, I, J, and F, as before, I don't want to write this the third time. So then this is homotopically equivalent to 0. So finally, let me define the ordered set that I'm going to use. Ordinal such that, so I take the cardinality of the disjoint union of the integers of the cones from the R shifted by P to the E. And this has to be strictly smaller than the cardinality of this ordinal gamma. And I, so is the set of all ordinals strictly smaller than gamma. So this is my set I defined by this ordinal gamma, and finally the object Bm that I want to consider will be by definition just the B gamma in this directed system. So construct this huge directed system which is parameterized not just by some finite ordinals, but potentially this could be non-countable ordinals, etc. So NVM is by definition B gamma. So the idea, of course, behind this definition is 0, right? So we constructed this iteratively, trying to kill, when you take in this distinguished triangle, you go from this map to this object BS, you kind of kill all the maps that you have in the previous step. So the idea is, at least intuitively, very clear, but of course to work out the details, at least finite induction, is not so easy.
Yeah, but you rename I, so you already use I, you now say that it's the set of all smaller than delta.
Well, this whole inductive process makes sense for any well-ordered set. And now I just choose my ordered set to be this set. And so I have this object, I choose the ordinal gamma, I take this well-ordered set, do this procedure until I reach B gamma, and that's by definition the object Bm that I want to consider.
So Bm is not colimit under this direct system, it's just B gamma. Well, it's kind of colimit, but okay.
Well, it's whatever you get when you do the computation. Okay, so that was the step one. I defined this B gamma by the transfinite kind of recursion. Now in the step two, which is the longest and the hardest step in the proof, is to show that the Bm is what is called L local, but let me see, be more precise. So this is in the right orthogonal category. Okay. So what we need to show in this step more precisely, right, to prove this claim, is that if I take a map, let me call this G, from the E shifted by K, right, to the Bm. So that's any map. So we want to show that G is homotopy to 0, right? This claim that we want to show is equivalent to the claim in the step. Okay, so to do this, I construct new directed system. So I take Vi. This is mapped with the map mu I gamma to the Bm, which is not the same as B gamma, so this is just a map in the directed system. So here I have a map G, so there is an image of G, which is kind of embedded here as a sub-object. And then there is Bi prime, which is defined as a pullback.
May I ask one question? So if we show that G equal to 0, we understand that so why it's all localizing subcategories that contains E? So why is B lies in orthogonal to all localizing subcategory?
Well,
Isn't should like some products will be the same?
yeah, because what you can construct, well, you can check. Well, if you know this for this kind of generators, EK, right? Then how you can obtain this result for any other object in the localizing category generated by the E? Well, you have coproducts, right? If you know this property for the individual object, you immediately get this for the coproducts.
Yeah, that's true.
And then the other thing you need to consider, if you have a triangle with kind of
Yeah, the same, true.
yeah. So it's enough to look only at these generators. So, but I'm constructing the new directed system, which I'm going to call Bi prime, and that's the definition of this object and the objects of the directed system. And I also want to introduce notation. So this map here is will be a mu prime with the indices I and gamma, the same as the low arrow. And then I'll want to construct maps in this new directed system. And this is done by the universal property. Well, it's not enough space, so probably I need to write this one more time. Okay. So B prime, say S. Yeah, and I also have different indices, so I need to write this one more time. So this is I with the indices S and gamma to the image of G. This is to the Bm. So this is Bs. There's an so there's a pullback here. This is mu S gamma. Okay, so then you take some B prime with another index I. So I assume that I is less than S. So then here you already have maps mu prime with the indices I and gamma. So here you have Bi. So this is mu I S. Well, it follows from the definition, that's how I define this object, that this square with the vertex Bi prime is commutative, hence there is kind of unique map here, which I'm going to call mu prime with the indices I and S.
So we construct new transfinite induction, yeah, and new direct set.
Yeah, new direct system, yeah. With the, which I'm going to call B prime. Okay, so for this new directed system, we can notice one thing. We can compute the colimit of this new directed system. So colimit
prime I. Well, by the definition, so this is keep the colimit, but this was defined as this pullback for the two sub-objects, so this is just the intersection. This is what we call intersection in the abelian category, or in fact maybe any category, image G. Right, but then one of the ways to define, well, one of the conditions which is equivalent to for category being Grothendieck is that you can commute this colimit and write this as Vm intersect with the image G. So this is just the image of G. So in this case, we know what the colimit of the sequence is. This is just the image of G. Okay. Now this gets a little bit more technical. So I want to prove two claims. So claim 1, so this is still inside step 2. So inside step 2 I have claim maybe 1 with the Roman 1. And this is a little bit technical. It says the following. Suppose
Can you explain why colimit commutes with taking a colimit by?
well, that's the general property of a Grothendieck category. Again, in those lectures that you attended, this was one of the definitions, right? So that if you consider colimit of the intersection, this is intersection of the colimit and the image of the second subobject.
So it is a property of Grothendieck category.
Yes. So Grothendieck category has, I think, at least 10 different characterizations. One of them is this one. So suppose that for any S which is smaller than gamma, there is T such that T is between S and gamma, and such that mu prime ST is not epi. Is not epi, or I can also equivalently say it's not isomorphism. These two conditions are equivalent since we know that all our maps are automatically monomorphisms. So then for any S less than gamma, there is element T such that S is greater with T is greater or equal than S, and of course smaller than gamma, with the property that the mu prime T plus 1 is not epi. So this is kind of easy looking statement, right? If I know that I can find for any S another element greater than S such that the corresponding map in the directed system is not an epimorphism, then in fact somewhere along the way there are two terms in the directed system, T and T plus 1, such that the corresponding map is not an epimorphism. So essentially the proof will be more or less by the contradiction. So assume by contradiction that for any T such that I have two inequalities as before, as in the statement, the map mu prime with the indices T and T plus 1 is an isomorphism. Okay, so then I can take minimal T such that S is less than T, T is less than gamma, and mu prime ST is not an epimorphism. So again, consider two cases. So in first case, T is Q plus 1, so this is a successor ordinal for some other ordinal gamma. But then, some ordinal Q. But then I have this kind of trivial formula that the mu prime S T is equal to the mu prime Q plus 1 and the mu prime S and Q, right? But this is now an isomorphism, and that's a contradiction. Right?
Mm-hmm.
Because Q is smaller than T, and we choose T to be the minimal.
Mm-hmm.
So this is the case when we have a predecessor ordinal, and now we have a case where this is a limited ordinal. So if T is a limit ordinal, well, if this is the limit ordinal, then I can consider the set Q of ordinals which are kind of between S and T. And this is clearly a cofinal subset. Of all ordinals in the ordinal T. And then object B prime with the index T, which is the colimit of the B prime Q, where Q is less than T. Or I can as well say that this is the same colimit for the Q between S and T. Right? If I take a colimit, I can take the colimit of a cofinal subset, it's still the same colimit. Okay, so now finally the end of the argument. So given ordinals, I have S and then have ordinal Q, and I have some ordinal Q prime. So Q is less than Q prime is less than T. So for these ordinals, we can conclude by our choice of the T is that the mu prime with the S and Q, and also mu prime with the S and Q prime are isomorphisms. So from this, it follows that the mu Q prime, so mu prime Q prime, which is equal to the mu prime S Q prime, well, it's easy observation, right? So this is just this composition, and this composition is the composition of two isomorphisms. So this is again an isomorphism. So that's an isomorphism. But now this object BT, right? That is a colimit over some directed set in which all the maps are isomorphisms, right? So, but then in the colimit, so in the mu prime Q T, right? So this maps in the limiting cone. So this is an isomorphism also. But if this is an isomorphism, then mu prime ST, which is the composition of the mu prime SQ and the mu prime QT, right, is again an isomorphism.
Why is mu prime QT iso?
What? Where?
The second to last statement.
This one? Yeah, that is because I have now BT is just this colimit, right? And then this colimit, I noticed that all the maps in the directed system are isomorphisms. Hence, it means that in the colimiting cone, all the maps are also isomorphisms. And these are the maps in the colimiting cone. Yeah. So that's an isomorphism and that's a contradiction. Okay, so in both cases, in the first case by kind of easy argument and in the second case by a little bit harder argument, we get a contradiction. So this proves the claim 1, right? And why we need the claim 1? Well, because I can, by this claim, I can conclude that if I introduce this JS with the index S, which will be by the definition of the sets of the ordinals less than gamma, and such that T is at least S, and mu prime T plus 1 is not an epimorphism, right? So this is non-empty.
So why is it so?
Hmm?
Why is it so?
Well,
Do we know the first conditions that there exists such T that mu prime ST is not epi?
it's not. Yeah, so I assume that. So yeah, so if I assume this, right, then this is not epi. From the claim, I get the conclusion that this is not not an isomorphism. This is what I do. I want actually at the end I want to get a contradiction with this, so then I can conclude that this is not true. So all of them are actually isomorphisms.
How we know that the GC is not empty?
Because, well, by the assumption, I assume. Well,
So we're still in this assumption.
yeah. So I still want the plan of the proof of the following. I assume this. I see what I can derive from this. In particular, I can derive that this is J sub S not empty. I can derive something else, and then at the end I'll get the contradiction, and then I can say that the original this part of the claim that is before then in this part is not actually true. We get the contradiction with this. So I can introduce this J sub S, which are not empty, and in particular, what's important is that I can consider set J, which will be just the J with the index 0. So this is cofinal subset of gamma at a special case. Okay, so but this doesn't finish the step 2. I need to erase something. So maybe I erase this proof, and because I want to show another claim. So
1 minute. We want to understand the JS. Which is cofinal subset of gamma. Okay.
okay, so
is also a cofinal set of gamma.
well, I need just one. So for the rest of the proof, I need to choose one. So
But any is a cofinal set.
yeah, I think that's correct. I can erase this.
Yes.
Okay, so I'm erasing this. I'm keeping the claim 1. Now I want to formulate and prove claim 2, which is still inside the step 2 of the proof. So first of all, I have the following observation to formulate claim 2. So for any T, which is an object in this newly introduced set J, well, there is some integer P such that the mu prime with the indices T plus 1 and I take the component of this map on the level P, so is not epi. is not epi. So, and now this will be maybe a weird way to formulate things, but I prefer this way. So we can choose map H sub t from the R to the B prime P t plus 1, which does not factor through B prime T P.
Is it claim or no?
This we know. Well, this is kind of very trivial statement if you think about this. Since we know that how J was defined, so the J was all the t less than q, which is t is at least 0, such that the corresponding map is not an epimorphism. So it means that at least I can find at least one level on which this is not an epimorphism. This is just in the category of complexes. If this is epimorphism of the between two complexes, it means that this epimorphism on each level.
So you mean it's P, it's
component in the complex.
Of complex.
Yes. So at least there is at least one P where this is not an epimorphism, and so since it's not an epimorphism, well, there is an element here, right, that doesn't come from this module. But I just choose a little bit weird way to formulate this by saying instead of the considering element, I consider a map. And instead of saying that there's element here which is not mapped, which is not in the image of the map mu prime from this, I formulate it like this because, well, it's actually the reason for this is I can generate this in this category. I have one projective generator, namely the ring, but if I can do the same kind of argument for any number of projective generators and get the ringoid, so it's kind of hidden reason, but it makes sense as a kind of precise mathematical statement. Okay, so this is I kind of fix this choice of h sub t for any t, and then I define a map. So define a map phi from the set J to the disjoint union of sets. So disjoint union over all integers of the home R, and then I have image of G, and again in this complex I choose the component with the number P. So this is defined as follows. So phi computed on the element T is the composition of the mu prime T plus 1 gamma, and again I take the component with the index P, and the composition is HT. That's the definition. So the claim map phi is injective. Okay. So let me suppose again that this is not the case. Suppose I have t less than q, and phi of t is equal to the phi of q. Without loss of generality, I can assume that t is less than q, and the images coincide. Okay, so the computation is essentially by looking at one commutative square. So I have b prime with the index t plus 1. This is mapped to the b prime with the index gamma. So everywhere I want to consider just the modules that sits in the degree p in the complex. So here this is the mu prime with the indices t plus 1 and gamma, and again just one component. So here there is h sub t from the R. Here there is h sub q to the b prime q plus 1 b. So there, of course, there is a map mu prime with the indices q plus 1 and gamma component with the index p. And then there is a map here, which is just mu prime t plus 1 q plus 1 component with the p. So clearly this is a commutative square, and this upper triangle is also commutative. Well, upper and right triangle is also commutative. Okay, then I have the following kind of silly and annoying computation, that the mu prime q plus 1 gamma, mu prime t plus 1 q plus 1 composition with ht, for by tautological reasons this is the same as the mu prime t plus 1 gamma ht, and also by the commutativity this is the mu prime q plus 1 gamma h sub q. Now I can notice that this mu prime q plus 1 gamma, by the construction, these are all monomorphisms. So I have this cancellation property, and I can cancel this and get that the mu prime t plus 1 q plus 1 composition with ht is equal to the hq. So this hq I can consider as a composition. There is r h sub t, there is b prime t plus 1 p, there is mu prime t plus 1 q, and this is b prime q p, and this is mu prime q plus 1 to the b prime q plus 1 p. So this composition of the last two terms, this is precisely the mu prime t plus 1 q plus 1. Right? So I can, since I have this formula, right, I can write this HQ as this composition, right? But this factors through the B1 prime and this map. So B prime Q and this map. That's a contradiction, so it's not possible to have such factorization.
Why we can subtract mu prime q plus 1 gamma?
Well, because all the maps are monomorphisms.
Okay.
It was monomorphism in the original directed system, and also monomorphisms after pullback. So that's a contradiction, hence this is not possible, hence the map is injective. Okay. Okay. So let me say that if I combine this all together, I'll say that the cardinality of the set J, well, this is less or equal than the cardinality of the disjoint union of the integers of the home. So the home that we just computed, our image of the GP, right? Since we have this inclusion, we have this inequality for the cardinalities, and
can you explain myself why we have a contradiction here?
well, because by construction of this HT for any t, in particular for the Q, it doesn't factor through this object, but this is the map HQ,
Yes.
and this is factors for the B prime Q.
Yes.
Okay. And this is strictly smaller than gamma, but our choice of gamma, and by the simple observation that the image is just the sub-object. Right? So we choose the gamma when we find this gamma in the end of the first step. There was object E here, but this is the image of the, well, this is the image by some map G of the object E somewhere. So in particular, this is the quotient object, so it can be even only smaller. It can be have higher cardinality than the gamma. Okay. So if I assume that, continue to assume it's something from the claim one, right? So if I assume that for any S, I have this, so that for any S there is T such that this is not an epimorphism, I end up with this inequality. By the way, I need to write the cardinality of this is not the cardinal, this is ordinal of gamma, right? But I claim, well, first of all, that the gamma is regular. So why gamma is regular?
What is regular?
Well, regular for cardinality, it means that the regular for the ordinal, it means that if you take the cofinality of this ordinal, it coincides with the ordinal. So now we're going into set theory. So the cofinality is the same, but why this is regular? This is regular because this is a successor ordinal, and by Hausdorff theorem, every successor ordinal is regular. So this is regular by Hausdorff.
So by regular it means that there is no less ordinals with the same ordinality. Cardinality.
No, regularity is the following. You can define cofinality. Let's do this in 2 steps, right? The cofinality, well, for the ordinal, you consider kind of the subset, right? Which is cofinal.
Yes.
And you consider and you want to solve the smallest possible cardinality.
Yes.
If this is the same as the cardinality of this, then the smallest possible the small ordinal with the smallest possible cardinality is the cofinality of the ordinal gamma. If the cofinality is the same as gamma, then this is called regular. And our ordinal or cardinal, doesn't matter, is regular. By the way, we constructed this. We take the cardinality of some set and then take the second, well, the smallest after that. So this is a successor ordinal by the construction, and by Hausdorff's theorem, every successor ordinal is regular. So this is regular.
So everything is isomorphism. Okay. So it's
Yeah, so we get the contradiction, right? So on one hand, by the result of our computation, starting from this assumption.
Gamma should be equal to cardinality of J, and it's
Yeah, so we have a strict inequality, right? But in fact, by the regularity in Hausdorff theorem, we have the cardinality of J is the same as cardinality of the gamma, and that's a contradiction. So we get the contradiction with the Hausdorff theorem. So it means we're almost done with the step 2. So I need to erase again something, and maybe I don't know. So maybe you have these claims 1 and 2 in your notes. Maybe I erase this part.
How we get that the cardinality is the same of J and gamma?
by Hausdorff theorem, because J is cofinal subset of gamma. Yeah, we proved it after we said it after we said what it's J, what J is.
Yes.
So and but it should be equal, and it's not equal.
Okay, so let me erase something
You
because
cannot erase, you can just map to the second page, and if you need these claims, you will
maybe that's a good idea. Okay, so finally, I'm almost done with the step 2. So I want to summarize. So that in the directed system, if you combine everything together, claim 1 and claim 2, so the direct system, B prime I, mu prime I j, maps mu prime I j are eventually isomorphisms. Right? Because if they are not eventually isomorphisms, we get a contradiction with Hausdorff theorem. So hence, at least I can claim that there is S0 smaller than gamma, such that the map mu prime S0 gamma, this is so the map to the colimit of the vi prime, which is the same thing as the image of G, is an isomorphism. So returning to the definition of the V prime, so I have V prime to the S0. This is mapped to the image isomorphically. So this is mu prime S0 gamma. So then there is some map here, which I don't have a name for this, so VS0 and mu S0 gamma V M. And there's some map here. So that's an isomorphism, so there is a map in the other direction.
So, is there such that mu S0 J prime isomorphic to colimit? What do you mean by map isomorphic to colimit? So there should be something that's
Yeah, so this.
missing something.
Well, I want to say that, so I want to say that this is an isomorphism, and this is the map from the. So this is a map from so this is just I'm thinking that almost out of time, and I don't want to do the end of the proof 2 weeks after today's lecture. So there is a map. So this map, what we can conclude from our contradiction, that at least we have an index such that this map is an isomorphism. Right? So the map that we considered in the beginning, so the map G that we write maybe one more time, so that is the map that we considered, so with the beta. So these factors through BS0, so this is BS0. Right? Well, this is I think clear from this diagram. So you have a map from the EK to the BM. You can see that this is a map. So this is somewhere, there's somewhere EK here, right? So there is a map here such that this composition is G, right? So instead of going like this, we can go like this, and this. But this is give you a factorization through the BS0. Right? So we can conclude that the G can be written as the mu S0 gamma some map G tilde. But this is more homotopic. Right? Since this is more homotopic, the composition is more homotopic.
We know that mu S0 gamma is not homotopic.
Yeah, because I constructed the direct system with two properties. All them have some monomorphisms, and all if you take any such map and the composition is other map, then this will be a null homotopic. So that's a null homotopic, and that's the end of the proof of the step 2, right? So when we have step 2, that the BM is L local. So finally, I have step 3, which is actually much easier. Step 3 is almost trivial. So step 3, so is the claim that the object NM is in the localizing subcategory L. Well, to prove this, I just introduce objects Ni shifted by 1, which will be by definition co-kernels in the category of complexes of the maps mu0i. So we will get short exact sequences. Since we have monomorphisms, we have M, which is B0, mu0i to the bi, and then the co-kernel is by definition Ni shifted by 1. So then I have a distinguished triangle, right? From any short exact sequence, I can produce a distinguished triangle in the derived category, Ni M map mu 0i bi and I shifted by 1. So that's the distinguished triangles that I want to consider. And also we can easily notice that if you take I less than j, then maps mu ij induces induce maps from the Ni to the Nj in the obvious sense, right, as the maps on the co-kernels. So then, using that the co-limits commute with the co-kernels, we can claim that if you consider n, m, right, then, which is the same as the n gamma, then this is the co-limit of the ni. So what I need to show to finish the proof is that all these ni's are in the L, because I know that L is localizing, and localizing categories are closed up under filtered co-limits. Right? But this is done by the octahedral axiom in a rather trivial way. So we have three distinguished triangles. We have M with the map mu. Maybe I write it. So we have it like this. So just again, using that this is a directed system, we can consider three maps. So we have three such distinguished triangles. So the first two are more or less by the definition, but two different indices. So there's I plus 1 here in the middle. And the last one, so how we get the last one?
Well, isn't it just definition of I plus 1?
Yeah, so the last one is, it's just,
Yeah.
So it follows immediately from the definition of the, it follows from the definition of the, of what? Yeah, definitely, sure. That's the thing that we have in the very beginning, so it doesn't require any new considerations, just what we have. So then I apply the octahedral axiom in a straightforward way. So I just arrange, so essentially I just kind of look at the octahedral axiom and apply it to this given three distinguished triangles, so I need just to write this in the right positions in the octahedral axiom. And I claim this is what you get if you do this.
There, so if we have an I that lies in N, and then an I plus 1 lies in N, that's true. But why, if we have N, not gamma, just delta, with delta has no successor, then N delta lies in L?
I'm not sure that I understand.
So we have a lot of ni's.
You're saying that for the, if you have a element and a successor element, this follows from the last distinguished triangle, right?
No, if you have, so what you showing that an I lies in L, yes?
Yes.
How you show it? You show it by induction.
Yes.
So if an I lies in L, then an I plus 1 lies in L.
Yes.
That's we showed. So,
I think that follows from the of this octahedral axiom, right?
yeah.
Because we have this distinguished triangle and we have this is in the L, this is in the L, hence this is in the
Yeah,
L.
that's no problem. But this directed system that have not only something that goes like gamma plus one.
Yes.
It also have something that has no
Yes.
successors.
Yeah.
How we prove that n delta with delta has no successors lies in M.
Well, because in this case, this will be a colimit, right? Maybe I write it here.
Yeah.
So it's not the end of the argument. So this as you mentioned exactly, this is how we go from I to the I plus one, right? So what we can say by this is that we have a claim that if Ni is in the L, then Ni plus 1 is in the L. This is what we proved by this dihedral axiom. So finally, the second case, so say if T has no predecessors, so then it means that the Nt is the equivalent of the Ni, where I is less than T. Well, and since this is a clearly Grothendieck category, we can rewrite this colimit as the homotopy colimit, and the homotopy colimit is in the L. So, in particular, the N gamma is in the L by these sort of arguments. So, as you can see, this is kind of not a completely trivial proof, but the result about derived categories of the Grothendieck categories can be very more or less, well, I will say immediately, we still need to prove something about the Grothendieck categories. Namely, next time I start with the Grothendieck, with the Pavlov integral, and then that's the way that it's theorem that says that any Grothendieck category is a quotient by a subset category of a category of modules. And from that result, I can more or less immediately derive everything about the Grothendieck categories. So there's still something that needs to be done, but this will be done in 2 weeks. So next week we don't have a lecture, so we meet again in 2 weeks. Is a quotient by a subset category of a category of modules. And from that result,